advanced transport phenomenon. So this today's problem and tomorrow's problem, we will see that okay, it will be mostly dominated by mathematical techniques, actually, how to solve the problem rather than physics. Physics is very simple. So that is what we are going to see. So take down all the information in given problem and we'll try to solve this problem. So here we have this gas A. So consider a gas liquid system as shown in figure. Consider a gas liquid system as shown in figure. So here we have figure. So this is kind of beaker, cylindrical beaker, which contains a liquid B and gas A. Okay. So here a gas A dissolved in liquid B. So gas A dissolved in liquid B and diffuses isothermally into a stagnant liquid phase in a beaker. So what is happening? This gas A dissolved in liquid B. So this will dissolve in liquid B and diffuses isothermally. So it means that a temperature of liquid is assumed to be constant and it is diffusing. So it means that diffusivity of A in B is constant throughout. So A is dissolved in B and then diffusing in liquid B. Diffusing in liquid B. A also undergoes a irreversible first order reaction. So what is happening? A also undergo irreversible first order reaction, homogeneous reaction. Homogeneous reaction means homogeneously it is reacting in this gas liquid mixture actually. So A plus B gives AB. So no catalyst is required. No catalyst is required. So A is diffusing in B, and while diffusing, A is reacting with B and forming AB with a volumetric consumption rate. So volumetric consumption rate is K1 double dash C. K1 double dash C. This will be the rate of reaction. It is given that volumetric consumption rate. Volumetric consumption, so maybe kilomole per meter cube. That is given here. Forming a high density solid. So it will give a product AB which is having high density. High density solid, and this is solid. So we have gas dissolved in liquid B. So homogeneously it is reacting, but product is AB, which is solid. So so as soon as it forms the product, it will not interfering in a reaction. That is what main aim, why it is mentioned that it is solid with a negligible solubility in A and B. So as soon as A react with B, it will form solid AB, and it is solid, hence it will settle down. It is not reacting again with this reaction A and B. So hence it is also given that this reaction is irreversible. Once AB is formed, that is nowhere to interfere with the reaction of A and B. If say AB is soluble in this A and B, so certainly it might give some reversibility and you may get an equilibrium constant, but this is irreversible reaction. So solubility of A in B. If DAB is the diffusivity of A and B, and L is the initial length of the liquid phase in a beaker. L is the initial length, and we can assume it is to be constant, and K1 is a rate constant. Develop the expression for concentration profile, average concentration, and rate of consumption of A under the influence of kinetics and mass transfer. Kinetics and mass transfer both are governing. So under the influence of kinetics and mass transfer, what will be the concentration profile of A? Here, average concentration and consumption, rate of consumption. If I calculate flux, so if flux is constant, you can calculate at flux any value of this thing actually, any length, and you can get the value of consumption of A under the influence of kinetics and mass transfer. So this is the problem. As I told initially also, first, so as soon as I started this class today, so here you will see how mathematics is important. So most of the time in transport phenomena, you will observe that mathematics will be more complicated than physics. So this today's problem and tomorrow's problem is kind of example. So as we are dealing with undergraduate transport phenomena, so we have not seen so many complicated mathematical treatments in our problem. It will be dealt with the physics of the problem only. So, but when you go to advanced transport phenomena, you need a very high skill in mathematics. High skill in mathematics, whatever you have studied in M1, M2, M3, then you might have studied partial differential equation, might have been studied in some subject. That everything will be used in advanced transport phenomena, and this is one of the example of the problem where you will see that this problem is very simple to solve physically. Physically, getting the differential equation is very easy. Once you get the differential equation, solving the differential equation will be difficult. Even after assumption, so many assumption, whatever differential equation you will get. So it needs a high skill of mathematics. And this is the general trend in transport phenomena, advanced transport phenomena, I will say, advanced transport phenomena. So you need to be equipped with a well-skilled mathematics. All mathematics you need to revise whenever if you are going for a higher study. So whenever you are doing transport phenomena, you please revise all mathematical courses because they are everywhere that mathematics will be very useful. So with this input, just I want to say that here it will be dominated by mathematics, this problem after all the assumptions. So now we will just reading all the problem. What kind of coordinate system will be useful here? Start with roll number 41. Mithilesh. Mithilesh. Roll number 42. Roll number 43.
Yes, sir.
43. Akash, yeah. Can you just revise the content of the problem and take out all the information of the problem? Just revise what is given in a problem. Can you read the problem once again?
Yes, sir. Consider a gas liquid system as shown in the figure. Here gas A dissolves in liquid B and diffuses isothermally into stagnant liquid phase in a beaker. A also undergoes an irreversible first order homogeneous reaction. A plus B gives AB with a volumetric consumption rate of K1CA forming high density solid AB with a negligible solubility in A and B. If DAB is the diffusivity of A in B, L is the initial length of liquid phase in beaker, K1 is the rate constant, develop an expression for the concentration profile, average concentration, and rate of consumption of A under the influence of kinetics and mass transfer.
Okay, first time
As
is which is our region of interest? Whether this is our region of interest or this is our region of interest? Akash?
liquid B,
Liquid B. So what kind of coordinate system will be suitable to solve this problem?
as this is given as a beaker, we can use the cylindrical
Cylindrical coordinate system. So in cylindrical coordinate system, what are the three directions? R,
R, theta, and Z.
R, theta, and Z. So whether now this will be R, this will be R, this will be a theta.
Yes.
Top view will be a theta, and this will be a Z. So whether concentration will vary in R direction, theta direction, or Z direction?
In Z direction.
In Z direction only. Why concentration is not varying in theta direction?
Uniformity.
Yeah. Akash?
Yes, sir.
Why concentration is not varying in theta direction?
So is the same liquid. Yeah, if we are considering Z direction.
Say, no. Why
Symmetrical.
concentration is varying in Z direction? That is fine. Whether concentration will vary in theta direction?
No, sir.
No. Why?
Symmetrical.
Symmetrical. Yeah, that is the reason actually. So you don't know. You are just guessing, and still that is correct. It is problem is symmetric around theta. Why concentration is assumed to be constant in R direction? Akash,
Yes, sir.
why concentration is assumed to be constant in R direction? Roll number 45, Prabodh.
Yes, sir.
Yeah, why concentration is assumed to be constant in R direction? Ca is constant in R direction.
Yes, sir. So, like the thickness of the boundary layer would be the same, and it's sort of symmetry again.
No. It is not symmetry in R direction.
So then, end effects are neglected. Maybe that's why.
Yeah, end effects are negative. I told this in first class itself when we are starting shell balance approach. There are not more than 4 to 5 logical reasoning. Why a certain kind of assumption we are taking. Logically, if you think about the problem, you get involved in a problem, you can clearly visualize why that assumption is logically true. So you can see that here certainly there will be variation in concentration in this region. If you moving towards the wall, nearby wall, so anyways, from center if you are moving, okay, you will see constant atmosphere. But near the wall, certainly there will be variation in concentration. Okay, of Ca. So it means that there is a variation in concentration with respect to R, but it is just near the wall. Hence, but I'm neglecting that, and that is why. What is the reasoning behind that? End effects are neglected. So, roll number 45, Prabodh, what will be the dimensions of differential shell?
So it would be the area of the cross-sectional area of the cylindrical beaker
Okay.
and delta Z.
Delta, very good. Now, as there is a variation of concentration only in one direction, this problem will be solved using two boundary condition. What kind of these two boundary condition will be needed to solve this boundary condition? Roll number 46, Aishwarya.
Yes, sir.
So, are you convinced that this problem can be solved if I get two boundary conditions? What will be the two boundary conditions needed? So this is why, this is what you need to do in all the subject. As soon as given the problem, you should expect what kind of solution you will be getting, what kind of information will be needed, whether that information is given in a problem or not. If not given, what kind of assumption can be imposed so that our problem can be solved with a given information. So now Ca is varying only in Z direction. So how many boundary conditions are needed, Aishwarya?
Two, sir.
two boundary conditions. So what can be these two boundary conditions first of all?
At liquid gas interface, the concentration will be P saturated by RT.
No. That is what very wrong actually interpretation yours is. Now we are interested in this region liquid. Okay, at liquid gas interface, you are telling a concentration of liquid in a first layer of gas that will be given by P saturated divided by RT. How to get the concentration of A in first layer of liquid, Aishwarya?
Sir?
So what you told is at liquid gas interface, the concentration of liquid in gas you told can be estimated by P saturated divided by RT. But at liquid gas interface, how to get the concentration of gas in liquid phase? Are you getting the difference? What is the difference? Why your answer is wrong? P saturated divided by RT.
Yes, sir.
So what will be the correct thing? I want at liquid gas interface concentration of gas in liquid phase. Anyway, first of all, tell me this problem can be solved by two boundary condition. What is general? What should be that general nature of boundary condition you need? Whether problem can be solved using two concentration boundary condition. Aishwarya?
Yes, sir. Yes, sir.
Whether problem can be solved using two flux boundary condition.
Two
If two flux are,
concentration.
yeah. If two flux are given.
Why?
Flux are given, whether problem can be solved.
Yes, NAZ.
Huh? NAZ
Yes,
is
sir.
given at two locations, whether problem can be solved.
Yes, sir.
You are not following transport phenomena. There are three combinations, either two concentration boundary condition or two flux boundary condition or one flux and one concentration boundary condition. Here roll number 47, Gurupreet. I'm not able to hear you, Gurupreet.
Hello, sir.
Tell me.
Yes, sir. We have two boundary conditions.
No, don't think we have. In general, you tell me.
Yes, sir. The problem can be solved if we have two boundary condition in concentration, or we have one condition in concentration and other in the flux.
Very good. One concentration and one flux. And whether problem can be solved using two flux boundary condition, Gurupreet?
No, sir. We can't solve it.
Yeah, this already we have seen in I think in momentum transfer. While discussing momentum transfer, this I told, because you will get a second order differential equation with respect to concentration. Second order differential equation with respect to concentration. Hence, problem can be solved using two concentration boundary condition. But while deriving this equation, I will get a first order differential equation in flux, and then differentiation of differentiation. So it means that if I use this one boundary condition of flux, that intermediate concentration constant will be called evaluated, then we will get a first order differential equation with respect to concentration. So one flux condition and one concentration condition is also enough. But as I am getting only first order differential equation in flux, problem cannot be solved even if two flux boundary conditions are given. This everybody should make sure. Okay, now here I need a two boundary condition. So Gurupreet, 7. So
Yes,
what
sir.
are the two boundary condition?
Sir, at Z equal to 0, we have concentration as Ca naught, and
C naught, and
at Z equal to L, the flux will be 0.
yeah, certainly you can see here after this there will not be flux of A. So at Z equals to L, flux will be 0. Okay, and at Z equals to 0, concentration is Ca naught. How to calculate Ca naught, Gurupreet or Hansaraj? Roll number 48, Hansraj.
Yes, sir.
How to calculate
Hello, sir.
CA naught?
Sir,
How to
CA
get
naught
the
will be
value
the.
of CA
Hello, sir.
naught? Tell me.
Sir, CA naught will be the solubility of A in liquid B.
Excellent, excellent. So, Aishwarya, did you hear this? Actually, it cannot be. You cannot get get this CA naught by P saturated divided by RT. This is the solubility of gas in liquid. That will be estimated by solubility of A in liquid B. Solubility indicates maximum possible concentration of A in B. So we'll assume that this first layer will be saturated with A. First layer of liquid B is saturated with A. So this is what. So this is if you are able to take out all this information. So now you can expect that you will be able to solve the problem. You will be able to solve the problem provided you are equipped with well mathematical tricks and all the information which you have studied in mathematics. If this much information you are taken out from this slide, so that's all. So you are able to solve the problem, you are able to get the concentration profile. Then once you have concentration profile, you can get the average concentration and rate of consumption. This can be related with the flux profile, and you can get all sort of mass transfer fundamentals. So with these informations. So with this information, we'll start this problem. Actually, this is enough actually in transport phenomena, and you should be you will be confident once you assume that okay, whatever needed information, whatever needed concentration profile. So and what is expected concentration profile? Roll number 49, Harshavardhan. Expected concentration profile. So where you will get highest concentration?
Sir, at Z equal to 0, we will have CA naught.
Yeah, you will be having CA naught Z equals to 0. Here you will have highest concentration, and at Z equals to L, you will have lowest concentration and some variation, some linear or non-linear. So if there is no reaction, so it will be linear variation. As there is a reaction, there will be non-linear variation. That non-linearity due to this reaction and all. So that is expected actually. So with this information, so we'll be able to, this is the concentration profile. So we are interested in concentration profile. Once you get this concentration profile, you can get average concentration and rate of consumption of A. So this can be estimated by NAZ. NAZ you can get it from flux, and flux at Z equals to 0. That will be a rate of consumption of A. What is the rate of consumption of A? That will be given by NAZ at Z equals to 0. So this is what concentration profile is there. Say concentration will not vary in R direction, A and effects are neglected. Concentration is not varying in theta direction because problem is symmetric around theta direction. Concentration will vary in Z direction only. There is a mass transfer of A only in Z direction. Concentration will vary in Z direction, and this will be governed by first of all mass transfer as well as kinetics also. If it is governed by only mass transfer, so you can expect this will be a linear variation of concentration. So as there is a consumption also, so certainly, so it will be non-linear variation. Okay, with this, differential shell. So what will be the differential shell? This will be the differential shell. So say S, say you can have S is a surface area into differential shell in delta Z. Okay, differential thickness in delta Z. Because my concentration is varying only in Z direction, hence I am taking a differential shell, this thing in Z direction only. So volume of a differential shell is S into delta Z. Surface area multiplied by delta Z. Surface area means from top, whatever with the circular cross-sectional area you can see, that will be a surface area, multiplied by delta Z will be the volume of a differential shell. And most importantly, this is given volumetric consumption rate per unit volume. Per unit volume, this will be given a volumetric consumption rate. Rate of A consuming, rate of moles of A consuming per unit volume is A consuming per unit time per unit volume. So that that is given volumetric consumption rate actually. Now, so whether reaction is happening in my differential shell. Here, roll number 51, Himanshu.
Yes, sir.
Whether reaction is happening in my differential shell.
No, sir. Hello.
Where reaction is happening then?
At the interface, sir.
Which interface? Here.
Gas or liquid interface.
So whether it is mentioned that okay, A is reacting with B with very fast reaction. So
No,
here they whether in this differential shell A is available.
Yes, sir. Differential shell A is available, sir.
A is available.
Yes, sir.
In this differential shell. B is
Yes, sir.
available.
Yes, sir.
So why there is no reaction in differential shell?
So, instantaneous fast reaction. No, no,
Where
sir. No,
it is
sir.
given, it is fast reaction.
No,
If it
sir.
is
No, sir.
fast reaction, the CA.
Sir, it
with,
reversible.
huh?
Irreversible first order reactions.
Irreversible first order reaction. But if this reaction is very, very fast, what will be the concentration of A in liquid? If it is very, very fast reaction,
Yes,
what
sir.
is expected concentration of A in liquid?
The maximum at interface, then it will reduce.
Why maximum at interface? If this reaction is very, very
Zero.
fast,
Sir, zero,
as soon
sir.
as zero, no? That is what? If A is reacting with B very fast, then what is happening? As soon as A is reaching here, it will be reacting, forming AB.
Yes, sir.
So the concentration of A in liquid will be zero all the time. But it is nowhere given that reaction is very, very fast. Reaction
Yes,
is intermediately. It will be controlled by kinetics as well as mass transfer. It is neither controlled by only mass transfer if reaction is very, very slow. What will be the solubility? What will be the concentration if reaction is very, very slow? Concentration of A in liquid.
Yes, sir.
What will
So
be the
maximum at the
concentration?
surface, and it will reduce linearly or non-linearly while moving down.
No, reaction is very, very slow. Mass transfer is fast. Reaction is very, very slow. So
Constant throughout. So it may be
constant
constant throughout. So
constant, and what will be that value constant? It will be equals to CA0.
yes, sir.
It will be linear, not linear, constant. So
Constant,
everywhere there concentration will be CA0. Everywhere concentration will be CA0 because mass transfer is fast, kinetics is slow. But here it is given that intermediate with some volumetric consumption rate K1 double dash Ca. So whether reaction is happening in this differential shell?
Yes, sir. As it is intermediate, will be happening, sir.
Yeah, that is what the previous problem and this problem. Previous problem we were dealing with a mass transfer in a small gas film around the catalytic surface. Around the catalytic surface, there we were discussing variation of concentration. This is not a catalytic reaction. This is homogeneous reaction. Homogeneously reaction is happening everywhere. The reaction is not happening only at particular place only. That will happen when you have catalyst involved in my reaction. Catalyst involved in that reaction means reaction will happen only at the surface of the catalyst. It will not homogeneously occur everywhere. Wherever, say, if A and B reacting in presence of catalyst, then it will happen at a catalyst surface, but it is happening everywhere, non-catalytic reactions, homogeneous reaction. So homogeneous reaction, everywhere reaction will happen. So this is the difference between previous problem and this problem. So in this also there will be a rate of consumption of A. So what will be the flux of A coming in this differential shell, Himanshu? How to get this flux of A coming in the differential shell?
So we can drive fixed law of diffusion too.
No, flux of A coming into differential shell balance.
Cell
So
balance.
writing a shell balance. Flux of rate of A coming in the differential shell.
So DAB into DCA by DZ. Flux of
DAB,
diffusivity of A and B into DCA by DZ.
Flux of A, rate of A coming in that differential shell. Rate will be given by flux.
Into
Flux
surface area, sir. Rate into
flux
surface.
into surface area. So
Surface area,
NaZ
sir.
at Z multiplied by what is the surface area?
So pi r square into delta Z.
Yeah, no, that is not a surface area. That is volume. What is
Sorry, yes,
the
sir. Volume, sir.
surface area?
Pi r square, sir.
Pi r square, or you can write surface area equals to S. S equals to pi r square. R is the capital R, radius of the beaker. Okay. What is the rate of A going out of this differential shell?
So flux at Z plus delta Z.
Multiplied by
Surface area, pi r square.
pi r square. And what is the volumetric consumption of A in the differential shell?
So K represent into CA
Yeah.
as
Because
surface area into
it is
delta
given,
Z. It is given, sir. Yes, sir.
it is given volumetric
Yeah.
consumption rate. This is volumetric consumption rate K1 double dash CA. And what will be the rate of consumption? This will be volumetric consumption rate, means this is per unit volume. And what will be the consumption rate of
So
consumption
we
in
will multiply it to volume.
divided by volume?
Achha, yes, sir. Divided by volume.
Huh?
Yes, sir.
Divided by volume or multiplied by
No, sir.
volume?
Into sir, we will divide. It is per volume, sir. So we will have to multiply it with volume, sir.
What is the volume of differential shell?
So surface area into delta Z.
Delta Z. So that is
Pi r
what.
square into delta Z.
So that's all. So you need to rearrange this equation, and this for binary system. Okay. So NaZ, all the time you will be getting combined equation actually combined. So yeah, roll number 52, Spandan. Spandan, roll number 52.
Yes, sir.
So this Na consists of two parts. What is this first part is indicating? What is the second part explaining? From where you are getting this first part, from where you are getting this second part. What is represented by first part? What is represented by second part?
Yes, sir.
So what is this first part? Spandan, your mic is off. Whether you are doing this intentionally or what? "53, Shivam."
Hello, sir. I'm audible.
What is this first part?
Sir, first part is the diffusibility of gas A to the liquid B. So we are considering the flux of that. And
Yeah, molecular flux. We are
yes,
calling it as a molecular flux. And what is second part?
sir, the second part is the reaction because of the reaction of the A plus B gives to AB.
This
So
is
that
not a
is
second part is not a reaction. Where is the reaction coming? Where is kinetic constant here? So we are into last but one class in transport phenomena. Still, you are saying that this second part is a reaction. So this is not a.
no, sir. Sorry, sir. It's like a convection flux, sir.
Yeah, it's a convection. So this first part is a conduction, conductive mass transfer or molecular mass transfer, molecular mass transport. And this second part is a convective mass transfer. In last but one class, you are not able to recognize this, means okay, this is not a good sign actually. You need to work hard. Everybody need to work hard. This is for NaZ. Okay, NaZ. And I'm taking this approximately equals to this. Okay, this approximately equals to this. What is the assumption from this step 1 to step 2, Jitendra? Jitendra, roll number 56.
Hello, sir.
What is the assumption I have taken? This equals to this. If this step equals to this step, what is the assumption considered?
The reaction involved in gas and liquid
So
interface.
where is reaction, man? Yeah, Aman. Devang.
Yes,
Yeah,
sir. Sir,
what is the
we
other?
have only molecular diffusion, sir, we have assumed.
Yeah, we are
We have
considering
neglected.
only molecular diffusion here. We are
Yes, sir.
neglecting convective diffusion. So whether this is the logical assumption for this, what might be the reason for this?
Hello, sir.
Devang.
Yes, sir. Sir, we have as there is, we have assumed, we can assume that there is no bulk motion.
Yeah, there is no bulk motion, or so here we are assuming a motion of molecule in a liquid. Okay, motion of molecule in a liquid, and that is not because of pressure difference or something. A is diffusing through liquid, and liquid is a B is a liquid, and liquid. So you can imagine liquid. A molecules will be compactly packed. Molecules of B are compactly packed, hence it is in liquid phase. So certainly the velocity of A in liquid B will be smaller. Velocity of liquid A, gas A in liquid B will be smaller. So that itself says that there is not visible bulk motion. Visible bulk motion is not there. Velocities are very, very small. Hence I can neglect this. Hence I can neglect this. And overall, this is governed by just a molecular flux. Okay, why? Because you can see a reaction involving gas, liquid, and solid. When gas is diffusing through liquid or gas is diffusing to solid, so you can neglect a convective diffusion. You can neglect a convective diffusion because liquid and solid, the molecules will be compactly packed. That itself will give the resistance to mass transfer. That will give you resistance to mass transfer will be higher, and velocity of the molecule for moment in liquid and solid will be very, very less. Less velocity, and less velocity means less bulk motion, negligible bulk motion, and overall mass is transferred because of this concentration gradient only, concentration gradient, and it will be given by just a molecular flux. This is clear to everybody? This is clear to everybody? Anybody has any doubt? Okay. So now this concentration is also changing. Total concentration is also changing. Total concentration means concentration of A and B, and it is forming a product AB. It is forming a product AB in my differential shell. So concentration is changing from in Z direction. So instead of this concentration constant, I can take a CA. Instead of XA, I can take a CA. So this is the fixed law of diffusion. Only here I am taking only fixed law of diffusion because it is assumed that because gas A is diffusing in liquid and solid, so negligible convection will be there. So convection can be neglected. Because negligible convection can be neglected, so it will be dominated by just molecular flux. So with this assumption, so we can apply a overall shell balance equation. So rate of mass of A coming in. So already we have discussed this will be flux multiplied by surface area at Z. So rate of mass of A going out, this will be a flux estimated at Z plus delta Z multiplied by surface area, and rate of production of A or consumption, production or negative production, you can say consumption by homogeneous reaction. So that will be equals to, you can see this will be NaZ multiplied by surface area, flux multiplied by surface area at Z, flux multiplied by surface area at Z plus delta Z, minus this will be volumetric consumption rate multiplied by volume, that equals to 0. Now dividing this equation by S into delta Z. Dividing this equation by S into delta Z, and delta Z tends to 0. So we'll get a differential equation for NaZ. Okay, dividing this equation. So S is dividing this equation by S into delta Z and taking delta Z tends to 0. And using the definition of differentiation, what I will get? D NaZ by dz. So this is this is minus, okay, multiplied by -1. Again 1 will be there, multiplied by -1. So you will get NaZ at Z plus delta Z minus NaZ at Z divided by delta Z equals to plus K1 double dash Ca. And that, using the definition of differential equation, this is what differential equation you will get. Okay, this is the shell balance equation you will get. This is clear to everybody? Anybody has any difficulty in this? Very easy. Now substituting the definition of NaZ, where convective flux is neglected. Okay, where convective flux is neglected, NaZ equals to minus dAB dCA by dZ. Okay, NaZ equals to minus dAB dCA by dZ. This is when this flux is dominated by a molecular flux only and negligible convective flux. So I can get this dAB del square Ca divided by dAz minus K1 K1 triple dash Ca. Actually, K1 triple dash Ca equals to 0. Now solving this differential equation. So that is what I was telling. Actually, this is not straightforward. Actually, this differential equation is a linear differential equation, second order linear differential equation. So even though it involves only one parameter Ca and one dimension Z, still it is not so easy. So there are standard solutions available for this. So for using that standard solution, initially we need to convert this equation into standard format. Standard format means, so so we'll see what is that standard format. So this is what equation we will get. This can be solved if I have two boundary conditions. So and these two boundary condition already we have discussed. So this one is a concentration at the surface is specified. Concentration at the surface is specified, that is there at Z equals to 0, Ca is Ca0. But this Ca0 cannot be estimated by Raoult's law, because here I am estimating concentration of gas in liquid. It will be given by solubility, maximum possible solubility at given temperature and pressure of gas A in a liquid. That will be a Ca0. And the second property, second boundary condition is at Z equals to L, flux will be 0, because there is a bottom of the beaker. Thereafter, the A is not moving. Thereafter, A is not moving. Hence, flux equals to 0. Or this can be taken as dCA by dZ equals to 0. So saying this NaZ equals to 0, or saying it is dCA by gradient of concentration with respect to Z equals to 0 is one and same thing. Okay, flux equals to 0 and flux is related to concentration by using a fixed law of diffusion in this problem, because convective flux is negligible. So these are the two types of boundary condition. So this can be solved using this type of boundary condition, as I told. So we can convert this into simplified differential equation of the type which is available in a mathematics simplified form. So for that we'll be using some dimensionless number. Okay, so we are converting this equation into dimensionless form. So you can use anything, okay, as per your convenience, and this problem can be solved just using simply dividing this equation by dAB and using one constant that equals to K1 triple dash dAB. Use any constant P. That problem you can solve. Okay, or this is actually multiplied this equation by L square CAB Ca0 into dAB, and using this is lambda. This is again lambda. So lambda Ca by Ca0. This is dimensionless concentration, and this is zeta Z by capital L. This is the dimensionless length. Now substituting this information, instead of Ca, lambda into Ca0, instead of Z, zeta into L, and rearranging the equation, what you will get? And phi equals to K triple dash K1 triple dash L square divided by dAB. This is Thiele modulus. This is called as a Thiele modulus. Now, if you remember, exactly same analysis is done with a problem in heat transfer. If you might have solved a problem which is discussing a heat transfer through fins, that was given to you as a homework. Okay, heat transfer through pins, there exactly similar manipulation is done. That term is also called as the Thiele modulus actually. Okay. So this is K1 triple dash L square divided by DAB. You rearrange the equation, substituting and rearranging the equation, you will be getting this equation. D square lambda divided by D zeta square equals to minus phi square lambda equals to 0. Now substitute everything and let me know if you are getting this equation or not. Substitute everything. Your roll number 59, Nikita.
Yes.
Yes, substitute all this definition. Okay,
Yes,
first
sir.
substitute for CA, then substitute for Z here, substitute for CA here, rearrange the equation and use the definition, this definition, okay, this definition I. So this equation should be equal to this equation. Just let me know if you are getting this equation or not.
Yes.
Lambda is a dimensionless concentration which is equal to Ca by Ca naught, and zeta is the dimensionless L length. This is not lambda, this is gamma, capital gamma in Greek. Okay, this is not lambda, this is gamma, capital gamma.
Excuse me, sir.
Yeah, tell me. Devang?
Sir,
Karthik.
sir, I'm Karthik, 85.
Tell me, Karthik.
Sir, by introducing this gamma, we will be further complicating the problem because further we'll get something in hyperbolic terms. But
yes, so anyway, the solution of this equation is in hyperbolic term only.
Sir, but I'm getting an equation which is linear and which is normal, but it is not matching with what we will get in
I
terms of
consider this is second order differential equation.
Yes, sir. So, like initially, we can write it in the form of d by dz into dca by dz. So, using the second boundary condition that z at z is equal to L, we have flux is equal to 0, which means concentration, rate of change of concentration at that point is 0. So, yes, sir, I've considered that.
Okay, it's fine actually. That is also true. That is also correct. But as far as I'm not expert in mathematics, but mathematician tells that this hyperbolic solution for this problem is more relevant to discuss the behavior of this problem.
Sir, but it would be difficult to verify. Now I'm
of this problem rather than so.
But
this again, anyway, you will get a logarithmic term.
Yes, sir.
So ln will be there. Again, you need to differentiate ln. That is possible.
Yes, sir. There is a way by which we can circumvent differentiating ln, sorry, integrating ln.
So ln that integration of ln term.
Sir, we can skip that section. As I said, that at a point we can assume we can write dCA by dz, and we have that.
Have you done that solution? Can you show that solution in?
Yes, sir. Yes, sir.
ठीक है 10 रुपए आपको आता नहीं तुमसे आता है जा रहे आप
हाँ sir, is it visible?
ये इतने दूर पैदल आ लेते हैं
हाँ now it's visible.
Sir, this
so where is CA? You go up.
Sir, here is the point where the equation starts. So now we can write it as integration of d2ca by dz square. So just by integrating this d2ca by dz square.
You check your video. You have now it's fine.
So by integrating this d2ca by dz square, we will be getting dca by dz. Up till now,
How
we have
come
not
this
completed.
CA? How can you take this out?
Sir, sir, we are keeping it aside. We are not integrating it.
How it is possible? Here also CA is there. Here also CA is there. How can you take this out? CA is not function of CA. CA is not function of Z.
Sir, it is, but we can include it in the next
No.
integration.
This is what wrong thing you are doing actually. This is mathematically wrong.
Okay, sir.
So this is not mathematically correct.
Okay, sir.
And in second, why you have taken this LAN CA then?
Then now for second integration again, I have put dca by ca. Then it becomes integration of dca by ca becomes LAN ca.
No.
And I've
Here,
sent the dz term there.
In first step before integration, you need to transfer this CA on LHS. CA on LHS and K1 divided by DAB is constant. Before integration and then integrate.
Yeah, yes, sir. I have probably logically skipped that thing. Okay, sir.
And then so that what is differentiation of LAN CA actually?
Differentiate in 1 by ca.
Integration.
Okay.
Integration.
Yes, sir. That's what the problem is. Integration of LAN ca.
That is what you have studied M1, M2, M3. So I'm not telling that this is the only way to solve the problem. There are more than one way in mathematics to solve the problem. But this might be a most suitable way so that you can catch the, you can say, description of the problem properly in the form of solution. So whatever we are taking this actually. So, and this already you have seen in PIN. That time also you have done same thing in PIN.
Sorry, sir.
In PIN, while solving in PIN, exactly same equation you got.
Yes, sir. But there also I was facing some complexity problem.
Again, you got similar equation when you are discussing, I think, a series reaction. When you are discussing a batch reactor study, series A gives B gives C. I think you will end up with similar kind of equation there also. So yes, this equation is not a first time you are seeing actually. This kind of equation I'm giving. This is one example is homogeneous reaction which we are discussing now. Second example is heat transfer to PIN. Third example is kinetic study in a series reaction. A gives B gives C. And when you are discussing a variation of concentration, that time also you will get a similar kind of equation actually. First of all, are you getting this equation?
Yeah, yes, sir. That equation I got.
This equation you got. So where 58. Yeah, 59. Nikita, you got this equation?
Yes, sir.
So now, once you get this equation, now you need to convert these boundary conditions also, so that it will be suitable for this gamma. This is gamma in terms of gamma and zeta. So z equals to 0, zeta equals to 0, z equals to L, zeta equals to 1, Ca equals to Ca0. So this lambda will be equals to 1. Not lambda, gamma will be equals to 1, and zeta equals to 1. This d gamma divided by d zeta equals to 0. Now for this boundary condition, with this equation, the solution, solving this equation, this is the solution actually. Hyperbolic solution, gamma equals to C1 hyperbolic cos of phi zeta plus C2 hyperbolic sine of phi zeta. So anybody remember this kind of mathematical equation you have studied in mathematics? Second order linear differential equation with constant phi. Anybody in the class? Exponential also, sometimes exponential also people will use. That depends upon situation to situation and boundary conditions. Now get the value of constant C1 and C2. So that is what I have started this problem with noting that. So here you need a detailed skill in mathematics. So you need to revise all the mathematics. This is what the case in when you are studying advanced mathematics. Advanced mathematics, so it will be dominated by advanced transport phenomena. It will be dominated by mathematics only. That time nobody will tell you how to solve this problem and why you are getting this solution, why using these boundary conditions and all. So this is all you are studied in all mathematics. Actually, you will be directly using this. So getting the equation up to this will be the transport phenomena. Hereafter it will be mathematics. So from here to here, if I give all the detail, that itself will take a couple of classes because I need to cover all types of differential equation, second order linear differential equation with constant, without constant, nature of constant, nature of boundary condition. Based on that, that solution will vary. So for this equation, this is the hyperbolic solution I am getting, and now evaluate the constant. So if you are very much interested in this, so you can go through this and get this, see the mathematics books, so how to get this solution actually. So what will be the value of C1? Roll number 60, Aditya. 60.
Yes, sir.
What is the value of C1?
Sir, I'm calculating. It's complicated.
So evaluating and substituting. So if anybody is getting value of C1, write in chat box.
Hello, sir.
Yeah, Aditya, tell me.
Sir, C1 is 1
C1 is
and
1. Very good. C1 is 1.
C2.
C2 is.
Yes, sir. C2 is
So you
minus
just remember
sine.
this is the d gamma by d zeta. Okay, this is
Yes,
not
sir.
gamma equal to, this is d gamma by d. First of all, you need to substitute zeta equals to 1 here and then differentiate this equation. That equals to 0.
Yes, sir. So,
And then
I
substitute C1, get the value of C2 from that equation. Substitute
C2
C1.
is minus sine h pi by cos h pi.
Sine h pi by cos h pi. No, I think it should be cos h pi divided by sine h pi actually. Yeah,
Sir, we are
yeah,
differentiating now.
correct. And substitute that equation C1 and C2 and get the value of lambda, gamma. This concentration, dimensionless concentration. Substitute C1 and C2 and get the value. Substitute and check you are getting this value actually.
Yes, sir. It's same.
Everybody is getting this. Now you need to go home. Okay, you need to go home and check what are the different type of differential equation you have studied. Why this is the same solution? Because here in CRE exponential equation, exponential solution also you have assumed. So in heat transfer also it was similar. Right? So this is the equation. So this is the concentration profile. So what is the concentration profile? So rearranging the equation. So if you rearrange the equation using the definition of hyperbolic, so hyperbolic cos and everything. So this is what you will get. So hyperbolic cos of I 1 minus zeta. So some definition of hyperbolic sine cos here you can use, and this will be a concentration profile. This is the concentration profile. So rewriting in terms of original form. So this is rewriting in terms of original form. So this is the concentration profile. Ca by Ca naught equals to hyperbolic cos of under root of K1 double dash L square divided by DAB 1 minus Z divided by L hyperbolic cos of K1 double dash K1 triple dash L square divided by DAB. So this is the concentration profile you will be getting, and the average concentration. How to get average concentration? This will be average over a length L. Average over a length L. So integrate it over from 0 to L divided by L. Integrate this concentration 0 to L divided by L. That will give you average concentration. So what will be the average concentration? So averaging this concentration in liquid phase. So this will be a integrating over 0 to L divided by L. This is L and this is integrating over 0 to L. This divided by Ca0. Here also divided by Ca0. Here also divided by Ca0. So this will give me average concentration. So mathematics play a very important role in transport phenomena. Transport phenomena means heat transfer, mass transfer, momentum transfer. In fact, kinetics, thermodynamics. So mathematics is a backbone of engineering. Not telling chemical engineering only, it's a engineering. Mathematics is a backbone of engineering. So whatever subject, whatever content you have studied in mathematics, that you should use. So that will be very useful every day, whenever you are solving any problem in any subject. So here some advanced thing is coming actually, and we should remember this actually. So what is the average concentration? Anybody got this average concentration? So average concentration is hyperbolic tan of phi divided by phi. Where phi equals to this. So phi is already defined. Hyperbolic tan of phi divided by phi. And don't skip. Okay, don't skip this kind of steps in your calculation. So here, because okay, it is assumed that already you have studied so many mathematics and this is complicated mathematics. If I want to go solution for this, I need to cover almost one class. How to, what are the different types of solution available, why this solution is framed, and what are the types of manipulation done. Hence, I am not doing this, but you should do all the steps. So this is hyperbolic tan of phi divided by phi, that will be average concentration, and rate of consumption, that will be NaZ. NaZ will be a DAB into dCA by dZ. Okay, rate of reaction. Okay, reaction rate at Z equals to 0. So NaZ and this minus DAB dCA by dZ. Okay, dCA by dZ at Z equals to 0. That will be equals to Ca0 DAB divided by L phi into tan H phi. This will be a DAB into dCA by dZ at Z equals to 0. After substituting Z equals to 0, you will be getting these values. Okay, do everything. First of all, what you need to do is, so you go home and search in mathematics. What are the different types of second order differential equation based on this constant value and boundary condition? You will be getting a different type of solution. Different types of solution here. Okay, different type of solution here. And then based on boundary condition, you will get this solution. This you need to work at home. This is your homework. And then getting this average concentration. Integrate this equation. Hyperbolic cos from 0 to L divided by L. Integrate this equation and get this equation tan H phi divided by phi. So use all the definitions of hyperbolic trigonometry, and then get the rate of consumption. Rate of consumption will be equals to NaZ estimated at Z equals to 0. Okay, reaction rate at Z equals to 0 minus. So differentiate this equation. And substitute Z equals to 0. So you should be getting this equation Ca0 DAB divided by L phi tan H phi, hyperbolic tan of phi actually. So this is all for today's class.